I don't usually do complex dynamics, so this is going to be colloquium-like talk, so everything will be defined, and hopefully I'll be able to answer all your questions. It's based on a joint work with Vaso Evredu and Letitia Pardon-Simon. Probably I butchered their last names, I apologize. And as guaranteed, let me start with the crash course, trying to place complex dynamics into the world that people here are more familiar with. Talking about dynamics, we usually have ergodic theory and topological dynamics. Ergodic theory, you talk about measurable actions of a group on a measure space, and topological dynamics, roughly speaking, is continuous actions of some topological group on a topological space. And so these are the objects and the questions we ask. So in ergodic theory, you talk about behavior almost truly, ergodicity, weak mixing, and so on. And in dynamics, in topological dynamics, you more look at like what things, the behavior on a dense set, minimality. Again, you have a notion of entropy, which sometimes is different from the one we use in ergodic theory. But if we classify things according to what we study or what questions we ask, then complex dynamics doesn't quite fit in either of those. So in complex dynamics, we study iterations of a complex function. So it's if we want to put it in the same context of an action of a group, that would be an action of the semigroup, which is the natural numbers. And you use an entire function to study it. So it could be entire, it could be meromorphic. And more than that, if it is entire, it could be polynomial or transcendental. So today's focus is transcendental entire functions. This is the cube. And the questions that we study are, what does the iterates behave like? Are they periodic? Do we have some kind of normality or chaos and so on? So now the key players, I think, in every dynamics talks are these two sets, the Julius set and the Fatou set. So let me define them. A point is in the Fatou set if you can find a neighborhood of that point such that the iterations restricted to that neighborhood will form a normal family. So a family of functions where for every sequence you have a converging subsequence. And if you're not in the Fatou set, then you're in the Julius set. Okay, the Fatou set is f of f, and the Julius set will be.
So I always forget that Fatou set is open, the Julius set is closed. Which one?
Yes.
Okay.
I'll say it in a minute, actually. So let's
That's why I remember.
see an easy example, and then
normal families again.
if you, for every sequence of functions, you have a subsequence that converges in the relevant topology. So for us, it would be local uniform. So easy example, z squared. If you look at iterations of z squared and you look at points that are inside the unit disk, they're going to shrink to 0. Points outside the unit disk are going to diverge to infinity. And so the Fatou set is going to be all the points that are there, the absolute value is less than 1 or greater than 1. And the Julius set is just going to be the circle. So as you can see, the Julius set is closed and the Fatou set is open. Now, a little bit of history. These terms were claimed by two mathematicians, Pierre Fatou and Gaston Julia, who was his student. And the Fatou set is sometimes also called the normality set. So this is, you have some kind of normal behavior. And the Julius set is many times called the chaotic set.
The normal comes from complex analysis, not normal
Yes.
family of functions. Every sequence got a convergent subsequence on the smallest, on the complex.
And
Right. I mean, historically, that's when they first proved the Riemann mapping theorem. This was the missing ingredient that Riemann didn't have. That's sort of around that time. So Kerber was the first to prove it. Normal families entered there.
well, Fatou was claiming, or feeling like the more interesting things is going to happen in the set of normality, and Julia thought most interesting things are going to happen when the chaotic things are. And I think this example a little bit supports more what Julia said, because the Fatou set is empty.
So who was the student? Who was the?
So Gaston Julia was a student of Pierre Fatou. And the Fatou set is empty here. Now the Julia set can be empty, but only for linear functions and constants. So if you have a transcendental function or a rational function of degree greater than 2, then the Julia set is already not empty. It's a theorem. Okay, and the key ingredient that we're going to use today is Montel's theorem. That's basically one of the strongest tools that we have to show that a point is in the Fatou set. If you have a family of functions and all of them emit two values, then this family is normal. And I'm going to write here something that I will call Montel's corollary. So if I have a neighborhood of Z such that the iterates restricted to U all omit an open ball, then Z belongs to the Fatou set. And this is what we will later use to show something. Okay, some beautiful pictures. So in complex dynamics, they always have these lavish pictures.
So what, sorry, in the previous thing, the point at infinity is one of them, right? Holomorphic maps and not meromorphic. Right?
So in general, some people do study meromorphic maps. Today, we're only going to talk about holomorphic.
3 points, yeah.
And the definitions might be a bit different in some cases. Okay, so some pictures. So these are pictures of the Julia and the Fatou set for the quadratic polynomial. And we have here 3 examples. This is for the cauliflower, the basilica, and the dendrite. And I chose these examples because you can see that the Fatou component, so Fatou set is an open set. And you can look at the components of this set, the connected components. So in the first example, in the cauliflower, you see that we have one bounded component and one infinite component. In the basilica, you see that we have many tiny components and also one unbounded component. And in the dendrite case, so the third case, this one, you have only one component. You can see the differences. Okay, so now we're going to classify these points and we're going to look at 2 different classifications. The first one is classification according to the Fatou component that you belong to. Okay, so Fatou components, they could be attracting. Attracting means, so they're attracted to a fixed point, which is a p-periodic point. So f to the power p of that point is again that point. And you can have an attracting, that's when the entire component, kind of the iterates shrink to that point. You have parabolic. So parabolic, it's basically the same, but instead of shrinking into a point inside the domain, you shrink to a point on the boundary. Basically, that's what you should think of. Then we have a Siegel disk. This is basically when f to the power p is, that's basically a rotation. So it's going to be analytically conjugate to a rotation. We have Baker domains. This is where these iterates converge to infinity. These all, I intentionally made them in purple because they're all periodic. So this P is the period. You can see it appearing in the.
So wait, since I'm trying to understand what you're saying, Siegel, I know why it's called Siegel disk. Baker is because of Baker transformation or somebody called Baker?
I think it's because of Baker, the person.
And what is going on there in this Baker domain? Can you say it again?
Yes, so these iterates just tend to infinity. So these are going to be unbounded
Okay.
because they're periodic, all of these 4. These are going to be unbounded domains and they're just going to go to infinity. And the last one, you see it in black, wandering domain. That's the only one which is not periodic. And this is just when the iterates are disjoint completely. So this is the first classification. So we have attracting, attract. Siegel, Baker, and wandering domains.
And what's the difference between polynomials and entire functions in terms of this classification?
Oh, that's a great question. So these are all periodic. And polynomials could only have these 3. So rationals in general, not just polynomials, rational functions can only have these 3. So these two can only work for transcendental. Okay, so again, a little bit of history. So when you Google this classification, I believe the first place that it appears is in a paper of Sullivan, where he shows that for rational functions, there are no wandering domains for rational functions of degree greater or equal than 2. However, if you try to go back and find the proofs, you can see that Fatou in 1920 showed part of it, and Kremer in 1932 showed part of it. Both of them at the time did not know that a Siegel disk and a Baker domain could exist. So they just said, okay, these are the cases that can happen, and we don't know if these are even possible. These examples came much later. In general, the way these examples are constructed, there are a lot of techniques of approximation. So the first example of wandering domain, which is today's focus, was done by Baker in 76. Since then, many other people followed. I can mention some names. I'm not sure if it.
Can you say what entire function does it?
Sorry.
Is it true for every entire function that you can have? No, right.
No,
So
not-
which entire function does Baker make that does this?
Well, his construction was not very simple, but I will show today at least two constructions actually of such sets.
And you'll show us the entire function.
Yes.
Okay.
Right. So since then, a lot of new techniques have been developed to approximate functions, which is basically how this thing is done. I believe some of 4 techniques are like people use Runge's theorem, which is very classical, or Archelian, which is just the extension. Yes.
So your example of z squared from the last slide, wouldn't the outer component be Baker?
That is a good question that I knew the answer to that because I already had this discussion.
It's polynomial.
The only one that you can easily see what it is.
Yeah, so my collaborator is here. Letty, do you want to unmute yourself and oh, you can't speak. Do you want to write?
You can unmute now.
Yeah. You can unmute yourself now.
You can unmute yourself now. Also,
Hi, so for polynomials, we study them in the Riemann sphere, and then we consider infinity a super attracting fixed point. So it actually follows in the other category. So it's an attracting basin. Well, we have for Baker domains in the definition.
it's a special case of attracting basin.
Is Baker a
Yeah,
Okay.
no.
that's,
So for Baker domains, we have that this converges to infinity, which is an essential singularity. So it's different.
Right.
So
So
for
okay. So
polynomials,
I remember now what was the problem. So the thing is this. When you define what a Baker domain is, and you define it for meromorphic functions, then the requirement is that the limit point would sit on the boundary of your set. And for polynomials, the infinity is inside the set because we look at it as the Riemann sphere, right? So it's not on the boundary. For transcendental entire functions, because it's an essential singularity, infinity is going to be on the boundary of your set.
So I was saying Montel's theorem is usually 3 points, but it's 2 points because infinity was occupied by the definition. Because you're making it an entire function with an
Is
essential.
that answering your question?
I think so.
Okay, great. Okay, so some pictures. The first one is we look at this. So this is a family of maps, lambda x of z. And what you see here is you see these blue parts. So as long as lambda is less than 1 over e, these are attracting basins. These guys in the Fatou component, this line shouldn't be here. So it's just we duplicated the same picture twice because the idea is this is periodic. So there are infinitely many copies of this. This is how you should think about it. So the black lines should not be there. And these guys, so they're not, oops, sorry. So these guys, that's not exactly the periodic point. The periodic point is going to sit somewhere on the real line. These are the preimages of the attracting point. So you look at the attracting point, and then you look what goes to that attracting point, what goes to that, and so on. And these are like the extra deep blue stuff. If lambda is exactly 1 over E, then we don't have an attracting basin. And if lambda is greater than 1 over E, then you'd have more than one Fatou component. So here you can see these beautiful pictures are called contour bouquets. They're like, look like very, very thin lines. It's the Julia set. And the blue part is the Fatou set, all the blue part. A similar image, which is not exactly the same as this. Again, you can see the exponent playing a role in creating these nice bouquets. And you can see that, well, if the real part of Z is positive, then this term in absolute value is pretty small. And you see that the dynamics kind of marches to the left or right, depending on if you're facing it or your back. But that's going to give you a Baker's domain. And the third example that I wanted to show you is wandering domains. So these white beats are the wandering domains. The smaller parts and whatever's in between these hairs, that's going to be the preimages. So everything is a wandering domain here, but these are all bounded. So one of the things about wandering domains in these constructions that there are some that are not bounded. Most of them though are bounded. Okay. And today what I'd like to do is I'd like to present two problems that seem unrelated, but we managed to make some progress on both these problems using a new tool of approximation that we kind of brought into the world of complex dynamics. All right. So the second classification that we have that I will need, it's a different classification. We look at orbits instead of components. So one of them is bounded. The entire orbit is bounded. If you think about the cauliflower, if you think about this nice rectangle picture that I showed you, each component there is bounded if you exclude the infinity component, which is the attracting basin of infinity. We have oscillating. So that's when you have two sequences, one going to infinity and the other one staying bounded. So think of it, the orbit looks like this roughly. And we have escaping, that's when it converges to infinity. So what do we know about this kind of classification? So polynomials don't have oscillations at all, and the attracting basin will always be escaping, right? And the other components are going to be bounded, just by definition. Baker domains have to be always escaping, that's just by definition. And wandering domains, so we have examples of them being escaping and being oscillating. But one of the great open questions in this field is whether you could have one that is bounded. This is still unknown. Okay, so the first story is the story on permutability and fast escaping sets. So if you have a pair of
these kind of questions that you raise, that you say unsolved, where you allow an arbitrary entire function.
Yes, I don't restrict the
order, nothing.
for now. Later on, we'll also talk about the order. So we say two functions are permutable if, well, basically they commute. Okay, so F composed with G is the same as G composed with F. And because it's not easy to find the Julia set, it's interesting to know whether, let's assume I have two commuting functions. Can I assume that they're going to have the same Julia set? Because if I have that, then I can find somehow a simpler function to find the Julia for and use something that is conjugate to it. So what do we know about this question? So Fatou and Julia showed it already in the 20s, that if we have rational functions, then this is true. And the way they showed it, it's very like the way that they were thinking. So Fatou was looking at the repelling fixed points. So the Julia set is the closure of the orbits of expanding fixed points. And he just showed that if you compose G on an expanding fixed point, then somewhere on the orbit, you're going to get an expanding fixed point, and then just use the fact that these sets are invariant under the function. Julia, on the other hand, oh, sorry, this is what Julia did, because he's into Julia sets. Fatou, on the other hand, did exactly the reverse. So he showed that if you apply G to the Fatou set of F, you stay in the Fatou set of F. So the sequences, the iterates of G form a normal family on this Fatou set, and therefore we have inclusion, and then we use symmetry. But they both use strongly the fact that these are rational functions and nothing else. Baker and Yarmenko, they studied the reverse question. So let's assume that we already know that the Julia sets are the same. Are the functions going to be necessarily commuting or not? And they have some interesting results for polynomials. So basically for polynomials, if the Julia set is not something that is called rationally invariant, rationally symmetric, they have this condition of symmetry, then they will have to be commuting, but that's only polynomials and that's only for these special Julia sets. They also studied, they counted how many functions are actually satisfy these two conditions. So they're going to have the same Julia set. So they have some results on that. And in 2015, Benini, Rippon, and Stallard showed that the conjecture holds always unless you have simply connected fast escaping wandering domain. So simply connected, we know, wandering domain, we know, fast escaping is something I still owe you. But this is a motivation for why are we interested in studying fast escaping? So let me leave it like that. You don't really have to write it down. So what is fast escaping? Fast escaping is when you have a point that grows to infinity, not just escapes to infinity, but escapes to infinity fast. So let me first read the definition and then say a few words about why it's defined this way. So we only define it for transcendental entire functions. And we say a point is fast escaping if you can find a radius large enough and some iterate such that all the future iterates surpass the iterates of the maximum models. So what do? You start with R0, you look at the maximum over a ball of radius R0. And this maximum will be called R1. Now R2 will be the maximum of the absolute value of the function over a ball of radius R1, and so on. So instead we look at iterates in complex dynamics. So instead of looking at iterates of F, we look at iterates of the maximum modulus map in a sense. And you want the iterates of F to surpass that, okay, to be greater than that. Now for polynomials, all the points escape to infinity at the same rate. So it doesn't make any sense to distinguish between fast escaping and slow escaping. For transcendental entire functions, Baker showed that, yes, it was Baker, who showed that if you give me a transcendental entire function and some growth rate, which is less than the growth rate of the function, I can find a point that will escape to infinity at that rate. So it makes sense to distinguish between slow escaping, faster escaping, and so on. Okay, what do we know about that? So Bergfeller and Hinkanen, they defined this and they show that all fast escaping Fatou components have to be wandering. This is actually just a result of a combination of the classification that I wrote up here and something that Baker showed. So Baker showed that if you're in a Baker domain, that the points, the rate that they converge.
How does this relate to the order of the entire function?
Not yet. That's the second story. Right, so Baker showed that if you have a point inside a Baker domain and you try to find the rate that it escapes to infinity, that rate is going to be polynomial. The polynomial will depend on the initial point. But yes, so these could not be fast escaping. So the only escaping guys could be wandering. Rippon and Stallard show that if a Fatou component intersects the fast escaping set, then it's already contained in it. So if I want to show that a Fatou component is fast escaping, so first of all, it makes sense to talk about fast escaping component, not just point. And if I want to show that a component is fast escaping, it's enough to find just one point. I don't need to work that hard to show it for all the points. And lastly, Baker and Rippon and Stallard show that multiply connected wandering domains are always bounded in fast escaping. And when I say multiply connected, I mean that they have holes in them, not that they have a few components. So if it's one hole, yeah, you get an annulus, if there are several holes. So not simply connected.
I have a stupid question about this definition.
I love stupid questions.
Okay, so if I take F and I shift it by a constant, like I add a constant to it, I feel like you should just shift the set of fast escaping points, but that's not clear from the definition.
Well, because your function is not linear. So if you shift your
Like I just replace
point.
F by F plus some fixed complex number.
Oh, okay.
Or is there like some,
could be completely different. You are not
Okay.
conjugating, you are just adding
okay, let me rephrase it. Why do you take the maximum over the unit ball rather than like the ball center to the Z? Like, is there some kind of extra symmetry here?
It's a growth rate relative to a center, which
It doesn't,
It'll change much.
it's not going to, why would it matter? Let's put it this way.
Maybe this doesn't make any sense.
Because after some time, you're going to include your point and then, right, I don't think it would change, like, I want to say that I don't think it would change the definition if I asked the balls to be centered at Z, it would just make the definition harder to follow. In the sense that maximum modulus is something that is very standard to study. This around the origin. Just because when you do talk about growth rate, then, okay, I don't want to say.
Most people make the center of the ball orange.
Okay, so what are known in terms of examples? So Bergler and Sixsmith, they constructed examples of bounded, simply connected, fast escaping wandering domains. So if you remember, the motivation for the question was this conjecture about permutable functions, and that was true always unless you have simply connected, fast escaping wandering domain, right? So we have bounded ones, and then the question is, do we need to think about unbounded ones? Yes.
I actually also have a question about the definition. So if 0 is an attracting point, then cannot I always find small enough R so that?
But this is why I say there exists R.
Yeah, but then there always exists sufficiently small R so that blah, blah, blah. So like almost every point that doesn't converge to 0 is fast escaping. It doesn't seem like what was intended.
Right, I think it's a typo. So the thing is, you can find a specific R such that, so you are right, we need to escape the attracting basin, right? Otherwise, so you're correct, R needs to be large enough. I should add there, large enough. Or maybe a different way to write this is if for all R large enough. Because once you pass one R, then, right, if you take larger R, it will correspond to a larger L.
If it is for all R other than there exists R, then it makes sense.
Yeah, so I think if you have R large enough, all R large enough would work. That's the thing. Yes, thank you. I'll fix it. Okay, so there is, as I said, we're going back to the motivation. The motivation was this conjecture that if you have commuting functions, then they have the same Julia set. And we know it's true unless we have simply connected, fast escaping wandering domains. So there exists an example of a bounded one. And because of that, Rippon and Stallard asked in 2012, can we find one with an orbit of unbounded fast escaping sets? And the answer is yes. So this is based on this joint work. So this is going to be theorem 1. There exists an entire function with a wandering domain. Actually, it's going to be wandering domains because all the orbit are going to be wandering domains that are fast escaping. Unbounded and fast escaping. Now, the first question that I would expect is, why don't you say that they're also simply connected? So Baker showed that if you have an unbounded wandering domain, it has to be simply connected. So we don't have to mention that, right? So this is the first result, the first half of the story. The second part is related to Baker's conjecture. So again, this is a very famous conjecture that I'll tell you about it now in the field. And it started with the order of a function. So we define the order of a transcendental entire function just to be this definition, which is, I don't know how easy it is to parse the formula, but essentially it means that if f is an exponent of z to the power q, the order will be q. Right? And you kind of get rid of all the logs and things that don't really influence. And the conjecture is, if you have a transcendental entire function, that the order of growth is half, then all the Fatou components are bounded. And we know quite a lot about this conjecture. So first of all, Baker already showed in the same paper where he made the.
Yeah, I have to ask a question.
Yes.
What's the effect? I don't know which is the closest, which is I would say for the Riemann zeta function. You know?
Sorry again.
Has anybody ever looked at the Riemann zeta function and its iterates?
I don't know.
take s minus 1 times z of s, it's an entire function, and iterate it, so it's order 1. That I know. Do you know the Fatou set for it?
I don't think so.
Okay.
Uh,
I'm just curious.
Why past, like what's
Okay.
something?
you learned something.
So I'll go to the next slide, maybe it'll be clearer. I think half came from the fact that he proved it for half, basically. I have some intuition for myself why it should be half, but I don't know if there's some theorems that say that it should be like this is a conjecture, so obviously there's no proof yet. But I will say in a minute, by the end of like this slide or next slide, you will see why now I more believe in half. Baker showed that if the order is strictly less than half, then there are no invariant Baker domains. So your Baker domain is periodic now, but with period 1, so you don't have several jumps, p is just equal to 1. And this is a very specific case. He also showed this thing. So if the order is less than half, and every convergent subsequence of iterates converges locally uniformly in the entire component. So you use the component to a finite function, then the component has to be bounded. So it's not enough that it converges in a neighborhood, like in the definition of Fatou set. His student Stallard showed that if the order is half, so here she almost got it. So you see that it's not order half, it's a little bit less. So for some epsilon, log of the maximum modulus is capital O of, so here we have the order half, and here we have some small error. Then also the conjecture holds. And in 2000, Zhang showed the case of rho equal or less than half. And he only showed it for periodic or pre-periodic Fatou components. So if we look at the list that we have up here of the classification, the only thing that is left to exclude are these wandering domains, because all the rest of them, the results earlier already took care of that. But that kind of, all of these results kind of come from below. They show that if you have an unbounded component, the order has to be at least half, right? But we don't have anything somehow topping this conjecture from above. So let's talk a little bit about what we know in terms of things that top it from above. There are, this is another result of below. So here we have the same result, but the order here is 1. So we have additional requirements. You have real entire function.
What do you mean by that? Real
entire, that you have the same condition on Taylor series. So you can develop, it's a real function, but you can recover it from. But now you have, so you have somehow this extra requirements that it only has real zeros. And then if the order is less than 1, then we don't have unbounded wandering domains.
So real entire function means the coefficients are in the.
So it's a real function. And if I remember correctly, and you can recover the function from the Taylor polynomial. So we have convergence everywhere. And then studying the Taylor function actually gives you, the Taylor expansion gives you some information about the function.
I guess it's just real analytic and entire. Once you complexify it, entire normal.
But here you see that the orders, so if you combine this result with the result of Zhang, with this, so here Zhang said if the order is.
So that allows you to double the order, is that the point? If you real, is that what this is saying? Can you just go back to what the statement?
This one? So here the order is 1.
Then you can go up to 1.
Yes. But if you combine these two together, then maybe the right answer should be 1 and not a half, right? Also, we have the following example. So the one example that, several examples that we do have, they all have order 1. So until not too long ago, we didn't have any examples of.
By the way, the zeta function would fit into this real. So the order, and it's order 1, so it's going to be an interesting case for you. Because on the real axis, there's another function which is real and real analytic. It's in poly. You try to understand the zeros that way. and the function's order 1. And so it might be an interesting question what it is for Z.
Right, so the combination of like these two, I couple these together because the combination of these two make you wonder, is half really the correct answer? And we show that half is indeed the correct answer. So this is theorem 2. We show a general construction that for every epsilon, we can find an entire function of order exactly half plus epsilon that has an unbounded wandering domain. So this one here is just because the methods that it used was like, let me cook up a function in my brain and ta-da, it satisfies everything we want. But they did not use approximations because they didn't have any approximations tools that actually control the growth rate. So this is our theorem 2. So for every epsilon between 0 and half, we can find f entire of order half with an unbounded wandering domain.
So you can't sort of take the square root of another example. Is that kind of built into your method, maybe?
No.
Take f of square root of z, because that's where the real, I think. And how did Herman show that? That's Michelle.
I don't know what the tools he used to show it. There is one thing I want you to notice, that here I am talking about, I missed a word. So here, one of the things that are missing is that we have unbounded orbits. So what I said earlier is because it's unbounded orbits, I can say domains and not just domain, because the entire orbit is unbounded. Here we have one unbounded component and we don't know anything about the rest of the components. So they could be bounded or unbounded. And we couldn't sadly say anything about it. So in the time I have left, I'd like to talk about the technique, which is new to complex dynamics. So if we have scanned the techniques that have been used in complex dynamics so far, they used Cauchy integrals, they used Runge and Arquillian, Bishop, I want to say not too long ago, brought a new technique of conformal welding to show all kinds of approximations work. Very powerful tools, but none of them give you any control on the growth rate of the function. And the tool that we kind of brought into this world does. So just a general scheme of how they do it in complex dynamics. The first step would always be to choose an orbit of the wandering set. I call it a wandering set because the eventual wandering domain is going to be some perturbation of that set. It's not going to be exactly this. And many times you won't be able to tell where the boundary of the set is actually. So for our case, for this example, I want to choose the easiest sequence of unbounded sets. So I'm just going to look at strips. So here the domains that I choose are just going to be strips. Here on the other hand, I need to choose something smarter. And I'm hoping to be able to say something at the very end of why this is the choice. But the choice here, you take a sector of opening epsilon, and then you take a sequence of balls. And these balls are going to grow and go to infinity. And then the next step is to define a map. This map needs to be locally holomorphic. And this is going to be called the model map. So for this example, what we're going to do, we're just going to jump from strip to strip. So we're going to jump from here to here, from here to here, and so on. And I'm allowing myself this, I will call this pasting area. So I'm allowing myself some pasting area. And here I will send this entire sector to the center of the first ball to the second ball, the center of the second ball, and so on. And now the last step is to approximate this model map in a good way, because at the end, the set that we're going to get, as I said, is going to be some perturbation of this. So for example, here, what we're going to look, the set will look something like this, right? It won't be exactly these nice straight lines, but it's going to be some perturbation, and that perturbation depends on the approximation, how good we're doing it, and how well we're doing it. Right, and again here, so we're going to do something like this and like this. And one word before I say more about the approximations, notice that if I approximate well enough, then the orbits of these strips are all going to exclude, for example, this ball here. So we know we're getting a Fatou component, exactly because of Montel's corollary that you have on top here, right? If the entire orbit, a neighborhood, you take the iterations, you look at a neighborhood, the iterations under the restricted to that neighborhood, and they are all going to exclude this blue ball. Similarly, in this example, you can choose some ball here. And again, as long as my approximation is not terrible and has any meaning at all, I can avoid an open ball and get that I have a Fatou component. So as I said, the novelty of our result is not these steps. This is very standard. The new thing is the approximation method that I'd like to talk about now. So we are using Hermunder's theorem. Let me state the theorem. So if you have a function in G2 locally and you have a subharmonic function such that this integral converges, then you can find a solution to the d-bar equation, d bar alpha equals to g. But moreover, this solution has to satisfy this inequality. So let me switch in for a second for the other side and just write Hermunder's theorem. And I'm not going to write the whole theorem, just U sub SH stands for subharmonic. And we want that the integral of G squared e to the minus U converges. Then we have a solution. By the way, this is a solution in distribution, but it's not only a solution, it also satisfies this inequality. So e to the minus U. And one question that I sometimes get asked a lot is, well, if this is not finite, then this should still be true because then the bound is irrelevant. The thing is, in the proof, we use, Hermunder uses L2 spaces. And if this is not finite, then this function doesn't belong to the space and you can't really know that there's a solution. Like maybe we can know a solution using a different technique, but not using this. So we actually need the conversions. Okay, great. So this is the theorem, and how are we going to use it? So we have, again, 3 steps. Step 1, you find chi, which is one where you want good approximations. So where your wandering set is defined. It needs to be 0 where your function is not defined. So for example, if we go back to these pictures, I'm going to define chi to be 1 here and 1 here and so on. And it will need to be 0 somewhere in the middle here, because I'm using one definition of a holomorphic function here and another definition here. They cannot touch each other, right? So I'm going to have some kind of an open set that separates them, where chi has to be 0, a transition area from one to the other. And similarly here, so it's going to be 1 here, 1 in the balls, and it will have to be 0 somehow separating these sets.
That's chi, not G. You can tell us.
Sorry?
You're going to use chi and define G now.
Exactly. So that's the next step. So G is going to be the d bar of chi times H. H is our model map. And because H, we chose it to be holomorphic on H component, then the d bar is just going to be d bar of chi times H. And then I will use Hermunder's theorem with a subharmonic function that I need to determine later. We'll have a list of requirements for that. And finally, I define F to be just this difference. So let me write these 2 definitions here. We don't have them in front of our eyes. So F, we start with G. G is going to be the bar of chi times H. which is just d bar chi times h. F is going to be alpha minus chi, sorry, it's the reverse direction. Chi times h minus alpha, where alpha is the solution to a d bar equation. Okay, great. Now, how does all this help us? Well, this method allows us to approximate and control. So I'm going to look at, just start with a general point. And let's assume that this point is in a location where you can find a small ball where chi is exactly 1. So if we go back to these pictures, what kind of good locations could we have? So these locations are good locations. All these guys. This is bad location. So I wouldn't choose anything here. Okay, and similarly here. Everywhere that I marked red, if you can fit in a ball, it's a good location. If you are too close to the boundary or you're outside, that's like a bad location. And then if you do a simple computation, you see that, well, because chi is equal to 1, if you look at the definition of f on the board over there, if chi is equal to 1, then f is exactly h minus alpha. So if you move h to the other side, you get a holomorphic function. Alpha will be holomorphic on these balls. And then you can use a version of Cauchy integral formula and get this bound, where the constant here, so this constant here, actually comes from the integral that you have over there, from this integral. So this is going to be the constant, basically. Maybe up to 2 or 10, but basically it's going to be as big as this. And why is this good? So if we look at this expression here, well, some part of it seems to be very big. This seems to be very big. But if your subharmonic function u is chosen such that it's very negative on this ball, because notice it's a ball that is about the point z, and this is about the point z. So if we make sure that in these areas our subharmonic function is very, very negative, we're going to get a good approximation. So this is one requirement that I'm going to have on my subharmonic function. On the other hand, I can make a similar computation for any point, but then I will have this additional term here. So you see that this bit looks kind of like it looked on the top, but then you have this is just the maximum model of the model map. And you can see here a bound on the growth. So if I will choose my subharmonic function smart enough such that the exponent of half the maximum modulus of the subharmonic map is comparable with the maximum modulus of the model map. So you see this relation. If they're comparable, in a sense, the growth of f is optimal, because f is going to grow roughly like the model map, and here you don't add a lot. You only add a constant and maybe a polynomial. So you don't damage the growth rate. Okay, so for our subharmonic function, we had 3 conditions. The first condition was to be able to apply Hermander's theorem. That was that integral over there converges. Okay, that depends on g. The second condition is where you want good approximations. You will have u negative, very negative. And the third one is you want the growth of the subharmonic function to be not too big, to be controlled by the one of the model map. Okay, and the last thing I want to say is I want to return to this.
Permutability theorem very difficult. So I have no intuition for this. Like, how should I think of this? It's like, is it very difficult to prove? Is it easy? Is it obvious? I don't know. It's like
it's not obvious. So this theorem in general is true in several dimensions, which we don't. That is the hard part. If you look at it only for the complex plane, it's not hard. He basically uses like operators and inverse of operators and like general Hilbert space theorems.
It's an elliptic equation. D-bar.
sorry.
Yeah, it's part of the story of solving D-bar, as was said, in several variables. It's much harder.
Yeah, so in several variables, you look at forms, and it's the calculations are basically the same.
So this is like a more general.
Yes, this is like a baby version.
Here.
This is, it's very, very strong, and so one of the reasons I wanted to talk about this result is not only how nice it sits in complex dynamics, but also because I just heard a lecture this morning exactly about Hermander's theorem, and it's underused drastically. People use Runge a lot. People use all kinds of approximations that don't give you control over the growth rate of the function. And somehow this is kind of left out. There aren't a lot of works on this. But if you need an entire function approximated, then this is a really good way to go. The last thing I want to say relates to the 1/2 question order, or if you think of it,
So at this point, F is entire, right? I would, in your construction, you use, when you make F chi times H minus alpha, is it not holomorphic everywhere?
so a priori it's not, because the solutions are only in distribution. But then because specifically it's equal to 0, you can use the fact that subharmonic functions are defined to begin with distribution, and then it's subharmonic and superharmonic to attach them together.
So you, at this point, have your entire function,
Yes.
and it's got the growth, and it's got the local behavior that you forced in
Right.
terms of your wondering, and then you have no control in general on its order.
Right.
Now you're going to discuss how to control its order.
No, I do control its order. I control its order using the second part.
Right, but you haven't shown us that it's what its order is.
Well, the order depends on how you choose your model map and how you choose your subharmonic function, basically. But it does give us some restrictions. So for example, if I want any angle at all, I'm going to have at least order 1/2.
Yeah.
Right? If I want more than one unbounded component, and I want to use this technique when you approximate well, I'm going to have 2 rays where the subharmonic function is bounded, and that could only be possible with order at least 1. So this kind of gives us some kind of restrictions, at least on this specific construction. And that is it. Thank you. Thank you so much.
The order has to do with the square root. It is a square root, which is the least angle you can put there. So there are many theorems in complex analysis about behavior at infinity. If the angle is bigger than pi and less than pi, are they related to this?
I don't know.
Right, you know what I'm talking about. The behavior at infinity.
So it is my feeling that most people who tried to make these kinds of constructions did not use subharmonic functions at all.
Yeah.
Right.
Yeah, right.
So I think so far until our results, all of the methods to create a function with some control on the order was always like, oh, I guessed this function and it worked out. This is why it was very hard to move from order 1 to something less.
It might be worth looking at Michel Herman's example. He's always got something very interesting. So it was just that one explicit formula then. You quoted.
Yeah, it's my understanding that, yes.
Must have had some method to deal with.
I would say a lot of experience. So he has several examples and things, but maybe Letty has more input on this.
Sorry, could you repeat the question for me? I cannot hear very well. Yeah.
Michel Herman's example of order 1.
Yeah, so
It's
our
just a
technique,
function. What's he using? Yeah.
yeah, so our technique sometimes to build wandering domains is that if you have some attracting basing and then you do a lift by some exponential because of 2 pi periodicity, you then make it a wandering domain. You manage to create a wandering domain by modifying another function which has a Fatou component that made it easier to understand. So that's a common technique. I think probably Herman's example is like that. I think it's a lift of another function with another component.
It's probably a covering argument. Yeah.
Yeah,
Right,
that's
a covering argument. Yeah.
Mhm.
I'll tell you a funny story about that.
More questions? questions?
So wait, so those are examples. So in terms of Baker's conjecture, can you review, is it now, you've solved part of it?
No, so in a sense, what we did is a complementing thing. So Baker's conjecture comes from below. He says, if the order is less or equal than half, then there are no bounded two components. And we show that if the order is greater than half, then you could have an
Yeah, so what was his conjecture?
That if the order is less or equal than half, then you don't have an unbounded Fatou component. So all Fatou components are bounded. But in a sense, at least it tells you that it can't be order one.
Yeah.
At least we have the right number.
Yeah, 1/2.
But does this tell you something about this commuting conjecture that?
No, so that was a different, so
Yeah.
in a sense, we have two stories here. Here, one is constructing an example that tells you that in Baker's conjecture, probably the 1/2 is true, because if it's bigger than half, you have an unbounded wandering domain. And the other theorem, which is theorem 1 that I said, that's related to the permuting thing. So the permuting conjecture is true unless you have a fast escaping, simply connected wandering domain. And then this is the only case we have to deal with. Do we have to deal with bounded? Yes, there are examples, but do we have to deal with unbounded? Yes, here's an example. So it tells you what's left to prove.
So I have another question, maybe for you and your co-worker. Sullivan, when he was working on this, I just remember this from years ago when I used to be at New York. He had this dictionary between this and Kleinian groups and their limit sets, and whichever is the closed set, yeah. I'll never remember which one for two. Julia is the closed. For rational dynamics, is there an entire function dictionary? So he's got some very nice relations there that have developed they're quite advanced between the theory of Kleinian groups and their limit sets and Julia sets.
So I
For
think
rational dynamics.
I think McMullen is doing something.
Yeah, many, but for entire functions, maybe you, is there a subject just maybe entire functions?
No, we don't have such a dictionary. No, we don't. I guess I don't know, it's infinite degree maps. I don't know if that's why, but no, there's no dictionary. There's no such a
Order doesn't help. Okay. I mean, people have computed, I assume, or try to understand the Julia sets for some very special entire functions, right? I mean, do you know them for any? Like I was joking about the Riemann zeta function. It's a function.
Right, it's meromorphic, right? The Riemann zeta function is meromorphic, and these conjectures and things are for entire.
Now, there's a natural function which is entire. You get rid of the pole.
Okay, well, I don't know about this function.
It's going to fit into your real version. It's going to be real on the where all the zeros are supposed to be. So in that case, I'm sure that maybe there is some, I mean, I don't think it's got a number theoretic meaning, but it could be a cute example to study. So, I mean, like we're writing down there lambda times exponential, and that's understood.
Yes.
What other functions?
Sine of
Well,
z.
you have sines, cosines. Then any very natural, well, people usually restrict we have the singular values, right? So we have critical values and asymptotic values where our map fails to be a covering map. And that's mostly what determines the dynamics of the map, because otherwise we just have local homeomorphisms and we kind of understand it. So it's quite natural to restrict to the Spicer class, which is the functions that only have finitely many of the singular values, because for analogy with the polynomial case, although now we are in infinite degree maps. And also people study class B, which is when you restrict yourself to functions which have a bounded set of singular values only. And then that's where you prove lots of results. It's quite different from the polynomial case. You always have unbounded Julia sets. The essential singularity at infinity kind of changes everything. You study whether you have these curves to infinity, what's the topology of the Julia set. You can have really weird incompossible continua as connected components. When you join infinity, you might compute the dimension of this set. So for polynomials, usually the dimension of the Julia set is close to 1. Here is always, it's more likely that it's close to 2. So you look for other examples. Yeah, those are the kind of questions. You might look at specific maps like combinations of exponentials and sines and so on, or you can just look more generally, knowing what the singular values are and how what their dynamics are.
Okay, thanks.
Okay, let's thank the day again.